This is a quick overview of Chapter 6, which is environmental risk. And I've also posted a more extensive talk about this last topic, risk assessment. But if you could just skim through Chapter 6, at least the first three sections are engineers and risk perception, toxic chemicals, spend a little bit more time on, and then risk assessment, try to kind of read that one more carefully. But the front end you can kind of whip through pretty quickly. So hazards. There's a lot of different types of hazards out there. Whether or not those hazards represent a real risk, either to humans or to wildlife in the rivers or wildlife in the forest, depends on whether there's actual exposure to the hazard. So you need both hazard and exposure to that hazard in order to get a risk. But that being said, there are many types of hazards, human toxicity hazards, all different kinds in there, ranging from carcinogenic materials to birth defects, mutagenicity, where there's DNA toxicity, all kinds of different issues that you can look up on your own time. I'm not going to go through each one of those. There's also environmental hazards. These are, when they say environmental hazard, they're focusing more on the fish, birds, basically the wildlife. So there's aquatic toxicity for fish and phytoplankton and frogs. There's amphibian toxicity for frogs, there's avian toxicity for birds, so lots of this mammalian toxicity. So these are all very real fields that people study, because when new pesticides, for example, are released, they want to know what the effects are on various places, various players in the ecosystem. And there's other hazards, physical hazards, global hazards. These are all kind of the big picture hazards in the global side, and it's really not the focus of Chapter 6. Chapter 6 is really more on the left side of this slide, where we're looking at toxicity, either to humans or to the ecosystems. So green chemistry is preventing this kind of problem. Many of the building materials that we've used to date have a lot of toxic ingredients, and in fact a lot of them that you can buy today going down to the Home Depot have toxic ingredients. And you probably have started to notice that people are selling regular paint and environmentally friendly paint with less solvents in it. There's less exposure, less risk from you breathing the fumes coming from those paints. So the next generation of products and buildings will be more green. And we all know that UC Merced buildings are mostly green. So even if the materials cost more to produce, the idea is that they'll have a significant long-run economic benefits, and they'll do less damage to the world, both the humans and the ecosystem inhabitants. And Table 6.4 talks about some of the economic benefits. So these are long-term benefits from people staying well instead of becoming chronically ill from being in poor buildings, for example. Sick building syndrome, I don't know if you've heard about that, but in the past, and there's still some old buildings around that that are built with so many solvents and so many additives to their carpets, additives to the paneling, to the glue that holds the compressed wood together, and these buildings emit chemicals, and sensitive populations can just literally become sick by working in such a building. Risk perception is an interesting topic, and it's becoming more important in the social science world and in the cognitive science world in terms of how people understand and react to hazards. And we certainly have seen a lot of hazards and risks come to fruition this year, whether it be the wildfires in California or the hurricane string that went through the Gulf of Mexico and the Caribbean, and all kinds of things going on in the world that really are very real risks to people who are exposed to them. So in the past, engineers have performed risk assessment without really considering how people perceive the risk, because after all, it is sort of a scientific matter as to whether a body or some aspect of a body will react to a chemical. But more recently, the engineers also began to work with social scientists because it works with better, it works for better communication of risk. How do we get the risk across to the public if we know how they're perceiving it? We know what words basically to use to make them understand the seriousness of a risk, or sometimes to make them understand that something that they perceive as very risky is really not that risky. So often risk mitigation projects or projects aimed at reducing the risk need to be prioritized by cost. It would be great if we could build a seawall around Florida in order to protect it from future sea level rise and storm surges and hurricanes, but that's probably not going to happen. We probably have to work more on educating people on what the real risk is, how, for example, the storm frequency may increase in the future, and then let them decide and how they want to react in terms of fortifying their houses or moving further inland or leaving the state altogether. But this chart is kind of interesting. It shows kind of a typical result that people tend to perceive more risk in the context of unknown or poorly understood hazards. So the more they understand and know about it, the less they perceive the risk, or you could maybe say, speaking more loosely, you could say the less they fear it if they understand it. So if you look on this chart, you see things where the unknown is going up on the y-axis, the known is going down on the y-axis, low dread or low fear is to the left, and high fear, high dread is to the left. And so things that involve really high amounts of dread are nuclear accidents, nuclear fallout, radioactive waste. These are, people don't really understand radioactivity for the most part, but they do see about it, in fiction, in the movies, and they know it can do some bad things to you. And they hear about an occasional accident out there that's real in the world. And so they may fear this, even if they live nowhere near a nuclear reactor. Think of one on the left-hand side. Caffeine. So people maybe it's sort of right at the border of known and unknown. They know that drinking coffee or drinking Coke makes them feel better, and they tend to have very low dread about it, even though there might be some serious risk with drinking too much of that. I'd say let's look at motorcycles. Motorcycles fall to the left where there's low dread, where they're pretty well known. People understand what a motorcycle is, so it's way down on the knowns end of the y-axis. But when it comes right down to it, if you were a motorcycle rider who feared nuclear reactor accidents, I think that you were more likely to meet an untimely end from your motorcycle than you are for a nuclear reactor accident. Anyway, you could look at this chart all day. At least I could. I think it's interesting. So hazardous waste and toxic chemicals is really the main topic of the chapter. And toxic or hazardous chemicals can cause everything from death to birth defects, infertility, or just plain illness from reactions with the chemicals. They're all different, and the chemicals are different, and they cause different reactions. They target different organs or different parts of people or different parts of fish or frogs, fish or insects. So in the U.S., generators are required to track chemicals from acquisition to disposal. So and they're also required to release what's called a TRI, a toxic release inventory. The public has the right to know, and they're required to report on how much they're emitting. This ranges from a factory that's blowing out smoke into the public air, so they have to give regular reports, having tested that smoke as to what's the content and the volumetric flow of that is, how much they're loading off into the air, to the city's wastewater treatment plant, which treats the water, but eventually it leaves the treatment plant in a pipe, goes into a river, goes into a lake, and they have to report that discharge or release. So if you added all this up, you would see there's 3.9 billion pounds of these chemicals annually as of 2011 that are reported to the US EPA. Now, in the past, before the EPA times, in the 1940s, 1950s, there were not such laws as this, and this is how the environment can really go bad quickly. So we had some real problems with our air and our water as we got into the 1970s, but then we started to get our act together. Doesn't mean we've got all the problems solved, but we definitely track it better than we did back then. So an interesting website if you have a chance you can tunnel into this one all day as well. This is an EPA My Environmental Map where you can look at the environment. You can put in a zip code or an address. A little map will pop up here. If you can see, I entered the zip code for Merced, and you can see it popped up there. I asked for some releases, and so some blue points came up on the map, so you can click on those and you'll see what it is. But you can here on the end, I think I did water ones, and so you can see different measuring points in the sloughs around Madera County, the Merced River, and several different places, and so on. You can see the air quality. You can scroll down and see the energy consumption, health issues, and the climate issues. What's the weather like? What's it going to be like? And what's the historical weather doing? So the pretty interesting information, but this all stems from the requirements that this information be made public by the people who are discharging or storing waste in the ground, etc. You can learn all about where your landfills are, where potential problems are. Someday when you buy a house, this is a good site to use just to make sure your area is not going to have any surprises that will trouble you later. I should say, according to the text I wrote on the right, this was just sort of my impression that when I was using it at first, I thought it was pretty interesting and pretty useful, but then I kind of tried to put myself in the mindset of a person who does not have a lot of training, and I thought maybe the site might be a little busy. So it might take a while to learn how to use this site if you weren't familiar with some chemical terms and some hydrologic terms and some air quality terms. Environmental justice is another small issue. Well, it's not as a large issue, but it's a small part of Chapter 6, is what I meant to say. Environmental issues are very real. They stem from the observation that when you look at most populated regions, the dense toxic releases, the kinds that you would find on the website on the previous slide, tend to show up in neighborhoods of low socioeconomic status. There's a lot of reasons for this. One reason is these are sort of the older parts of the city, so that's where sort of the factories and the waste treatment facilities developed, and they happen to be there. And then the housing becomes more affordable there because it's not the cleanest part of the city, so the most desirable part of the city. So the lower socioeconomic people tend to get their houses there, and it's sort of a perpetual cycle that sort of perpetuates itself until all of a sudden it's very evident that you've got the clean side of town that's very affluent, and the environmentally degraded part of town that is less socioeconomically affluent. So this affects population. Also, the affected population may not be well informed or empowered to push for changes. They may not know their rights. They may be too busy working 3 jobs to deal with the problem. So there are non-government organizations. I know some of you in the class have expressed interest in the political and social sides of the environmental engineering world. And there are places like the Environmental Defense Fund that do very real work to advocate for these people. They know the rules, and they will go after companies on behalf of the populations in these areas. So toxic effects of chemicals. This is the real big part of this chapter. So there's 2 general effects in a big sense: carcinogenic and non-carcinogenic. So carcinogenic, I think we all have somewhat of a feel, or unfortunately maybe know someone who's had cancer. So carcinogenic causes cancer, the abnormal growth of abnormal or malignant tissue, all different kinds of not so severe, ranging to very severe. And then there's also non-carcinogenic, which is kind of a catch-all phrase that means any other toxicological effects or harmful effects besides cancer. So the less serious, less life-threatening range from just a skin rash from a chemical that irritates your skin, breathing something that's maybe a little bit acidic or causes a cough or throat irritation, or maybe gives you a headache, ranging up to nausea, chronic cough, all the way up to real damage, irreversible damage that can even result in death. So in terms of assessing the risk, there's two main factors. There's the exposure pathway and the dose. So this is, remember, we have to have a chemical that's hazardous, but assuming we do, then it comes down to exposure pathway. Is it being eaten? Is it being inhaled? Or is it thermal contact? And dose. How frequently is a person exposed or a frog exposed? And in what amount are they exposed? So some chemicals can be dangerous in more than one pathway, but perhaps, for example, if there is a chemical in the air, it's going to partition into the water, but so you're standing by a lake breathing this air, and inhalation is really the main pathway, because very, very rarely are you going to reach down and take a cup of water out of the river and drink it. So most of the time there's one clear pathway, but it doesn't mean that the chemicals cannot come at you in different pathways. Some toxic chemicals are basically bad no matter how they enter your system. So determining the toxicity, this is done usually by laboratory studies, and so this chart tells you what's called the LD50, and LD50 stands for the median lethal dose, or the dose at which 50% of the test population that is exposed dies. So this is this curve on the bottom represents the concentration where you have a bunch of rats in different cages, and in the different cages you give each one a different dose. And in the low doses, hardly any of the rats are going to die, maybe none of them. As you raise the dose, a few of them are going to die. And at some point you're going to hit a dose where half the rats in the cage would die. And sounds like a little bit of an awful test to do, but this is the way they do it. Because it's a mammal, and so it's certainly not a human, but it's a mammal, so some of the metabolism and some of the reactions are going to be similar. So it's taken as a good test. So you can see the potency of these different chemicals in the table. Down at the bottom is sarin, which is this awful nerve gas that's been used in war and threatened to be used in chemical warfare. And you can just see that at that very, very low dose, you got 50% death. Some of these are like dieldrin is a pesticide, lindane is a pesticide. You can see that these are, certainly it takes a much higher dose than the sarin, but it's still only 38 milligrams per kilogram of body weight is enough to kill a mouse. So this is an acute toxicity issue, something that happens on a short term, so hours to day. So this is basically poisoning, something that could really hurt you in a short amount of time. There's also a response that results from long-term exposure, weeks to years. This is chronic toxicity. So what happens when you have very small doses over long periods of time? And this is things like the air you're breathing every day, or the water you're drinking every day, where there's very low levels of things in there, and you want to know if this is going to hurt me in the long run. It's certainly not going to hurt you in the short run, because the short run is the acute toxicity, and that's where you drink the glass of water and an hour later you're dead on the floor. That doesn't happen with our drinking water. So chronic toxicity is where I drink it 5 glasses a day, for 30 years. How will that affect me? So we're gonna the other talk. I think it looks like I've cut off my slide a little bit here, but just to power through this, there's 4 components here of risk assessment, and I'm going to go through this in a worksheet in a moment too that you can look at. So there's hazard assessment. That's just the first step where you want to make sure there is a hazard. You're going to look at the chemical's information, the properties of the chemical, studies on the chemical's toxicity. Have people done rat tests or mice tests? Or if the best data is epidemiology data, where there's actually been exposure to humans. This is less common, but there are cases where chemicals are used in the past. Sarin, for example, the bad example, but other chemicals like arsenic, for example, is in the naturally in some of the groundwater in California. So in some places, the water has a little bit of arsenic in it. So we'd really like to know how arsenic affects humans. We know arsenic is a poison, right? Because there's a famous play called Arsenic and Old Lace. Arsenic and Old Lace, where they poison people by putting arsenic in their drinks. But at very low levels, how toxic is it? So there are places in the world where people have been exposed to arsenic in Bangladesh, groundwater, certain parts of India, certain parts of Taiwan, some of the well water there where people were drinking untreated water, basically did very large-scale epidemiological studies of the effects of arsenic. So we know that very well. Other things, we don't know it because you're not allowed to test it on humans. It has to be kind of an accidental exposure or we just know about it from some horrible exposure during war times or something like that. So after you, it's pretty quick, when you know what you're doing, to look into the papers and look into history and see if something is a hazard. And so then you move on to how strong of a hazard is it. And this is called dose response assessment. So dose is how much a person either consumes or breathes or absorbs through their skin. And response is the toxicological response, the bad response. So what kind of dose leads to what kind of response? So these are these curves that you build to see. And so the steeper the curve, basically, the more potent a chemical is. So the estimation process is done differently for carcinogens and non-carcinogens, and I go into that in a little more detail on the worksheet. So after you've got you've decided that it's a hazard and you have come up with some estimate of the dose response, so how potent is it, then you see if you can estimate how much is exposing your population, whether that's people or fish or frogs. And so you estimate the concentrations that would be out there, estimate the concentrations that are consumed, estimate how often someone breathes or how much they breathe a day, how much water do they drink a day. These are all good environmental engineering calculations. So the exposure assessment is particularly where the environmental engineer comes into play on this problem. So we can use the numbers from others, but we're not toxicologists, we're not epidemiologists. We often have to use the information from the other group, so it's kind of an interdisciplinary problem, we call it. So once you've got the dose response and the exposure assessment, you can put it together and give numbers as to whether there is a significant risk or not. So that's a quick overview of Chapter 6, and like I said, front end of Chapter 6, just get a rough idea of that, skim through it, skim through risk perception, look at toxic chemicals a little more carefully, and then try to really read the risk assessment part, and then look at the next one where I work slowly through some notes, and some of those are a little bit of a repeat of this, but you could fast forward over that part if you want, or just listen to it again if you want to learn it better. So that's it for now, and I'll see you in the next slides.